Hello, welcome to Keen Motion's course on understanding electricity and electronic devices. This is our class 7 part 4 and we're going to talk about switching regulators today. Let's review some of the concepts we saw in previous videos. Okay, so when we studied linear regulators, we did some calculations about power dissipation, right? And we ended up in that example that it had an efficiency of around 52%. So we were delivering 5 watts to the load and wasting 4.5 on the regulator itself. So their power losses in linear regulator can be very high. On another class, we also saw that inductors can store energy in the form of electric current and magnetic field. And when we had inductors in circuits with switches, we could generate voltages outside the supply voltage, right? Because they could act as current sources, okay? So today we're gonna have a look at switching regulators in 4 different configurations, which are the buck boost, inverting, and the buck boost, which is topology changing. And then we're gonna have a look at some pre-made switching regulator modules. So let's start by considering this circuit. It's a constant voltage source connected to a resistor and a switch that opens and closes, so several times per second, and it remains closed for a T on time, and then it opens for a T off time. If we were to measure the voltage on the resistor, we will end up with something like this, right? So it's at 0, then it rises to the input voltage, stays there during the on time, then it drops back to 0, stays there for the off time, and the cycle repeats again. So if we were to calculate the average voltage of this waveform, it would be governed by this equation, right? So by varying the relationship between the on time and the off time, we could control the output voltage. Now, this is not DC, right? Because it goes from 0 to an input voltage and then back to 0. So what we could do is we could add an inductor and a capacitor, right? And that would be averaging this, and this will give us the DC voltage that we are trying to obtain. In this circuit, we have also a diode here, but we're going to see what the diode is for in the next few slides. Bottom line is we can control the average voltage and we can use the inductor and the capacitor here to make the average voltage into a steady DC voltage. Something that we want to keep in mind is the switching element here. The switch that we saw was either fully on when it has a low voltage drop or fully off, right, when it has 0 current. So if you recall that power dissipated is the product of voltage times current, and we try to estimate what the power dissipated on that switch is going to be, it's going to be very low, because when it's fully on, it has low voltage drop, and when it's fully off, it has almost 0 current. So power dissipated on that switch is very low, and that means that the regulator that we had in the previous slide will be wasting very little power. So that means that the whole regulator will have a higher efficiency, and typical efficiencies for these regulators are about 85% or more, sometimes in the 90 to 94% range. Another interesting thing about these switching regulators is that the switching occurs at a very high frequency, about 100 kilohertz, and sometimes up to 1 megahertz. So if you recall from the class on rectifiers and filters, when we switched from the half-wave rectifier to the full-wave rectifier, the full-wave rectifier had double the frequency, right? And that allowed us to have less ripple with the same capacitor. So, and the full-wave rectifier has a frequency of 100 hertz in North America. So imagine what could happen if we increase that frequency to 100 kilohertz, right? So the capacitor could be pretty much 100 times smaller for that, all right? On the downside, if we, switching regulators are more expensive than linear regulators, and they are more difficult to make. So let's start having a look at actual configurations of these converters. This is the buck converter. It's this configuration here, and the output voltage, which is the voltage that we will be measuring here, is lower than the input voltage, which is the voltage here. And this is the same circuit we saw on the previous slide, okay? We have the switch that remains closed for T on time, and then it opens for T off time, and then it repeats. So how does this work? Well, when the switch closes, we have some current flowing through this inductor and charging the capacitor, and some of it flowing through the load, okay? When the switch opens, whatever current was flowing through the inductor will keep flowing through it, right? Because remember, inductors act as current sources, so they oppose us to changes in their current. So for a little while, they will work as current sources. So we have to provide a path for the current to flow, right? To keep flowing. And that path is going to be provided by this diode. So when we open the switch, there's going to be current flow in this direction. So the current stored, the energy stored in the form of current in the inductor is going to keep flowing into the capacitor and into the load, okay? And we're not going to get into the details of the math for this, but it can be demonstrated that the output voltage is the input voltage times the on time divided by the on time plus the off time, okay? So this thing here is sometimes called the duty cycle. So by varying the duty cycle, which is the relationship of the on time to the off time, we can control the output voltage here. Okay, let's have a look at the boost converter. The boost converter has this topology and produces an output voltage that is higher than the input voltage. And we briefly saw this one when we studied inductors, right? But let's have a look at it in a little bit more detail. So when the switch closes, we're going to have a current flowing through the inductor this way and then through the switch. The capacitor, we assume it's charged to some voltage, and therefore, when we close the switch, this diode is going to be in reverse and it's not going to be conducting. When we open the switch, again, the current cannot change instantaneously through the inductor. So the current is going to keep flowing through the inductor, and the diode is going to provide a path for it. So the energy stored on the inductor, it's going to be going through the capacitor and the load now. And if you remember from our class on inductors, this will result in a voltage here, which is higher than the initial voltage here. And it can be demonstrated that, again, the output voltage is the input voltage multiplied by a factor that depends on the on to off time relation of the waveform. So again, by manipulating the on and off time, we can obtain different voltages here. This one is a buck boost converter or inverting circuit. Now let's clarify something. Classically, this topology was called a buck boost converter. Nowadays, a buck boost name is reserved for something else, or used most frequently for something else that we're going to see on the next slide. But just to avoid confusion, I also call this an inverting topology here. So in this topology, the output voltage is going to be negative or reversed with respect to the input voltage. So let's see how this works. When we close the switch, we have a current flowing through the inductor, okay? Now, when we open the switch, the current keeps flowing through the inductor and now through the diode, and it kind of takes charge away from the capacitor and makes a current flow in this direction through the load. And that's what's going to be producing a negative voltage here. If you want the equation, again, it's going to be something like this. So it's going to be negative times the input voltage times the relationship between the on and off times for the signal that controls this switch. The last one we're gonna see is the buck boost converter topology change. So the buck boost converter is something that actually can change between being a buck converter and a boost converter. So this, what this does is it can raise the voltage or lower the voltage. So what is this useful for? So this is useful for instance, for battery operated devices. Let's assume we have a circuit that requires 3.3 volts to work, which is a fairly common voltage in digital circuits. And we have a voltage provided by a lithium ion battery. Lithium ion batteries have a voltage of 3.7 volts. Well, of course, this is when they are charged, but as they discharge, the voltage is going to drop, right? So when we have 3.7 volts, we want to lower the voltage to 3.3. And as they discharge and say they are at, for instance, 3.2 volts, we want the voltage to increase to 3.3. So this is a circuit that can take care of that, okay? So let's see how this circuit can change topology to act as a buck or a boost converter. If we keep this switch closed and this switch open all the times, we end up with an inductor connected to the capacitor and the resistor in parallel. So this section of the circuit is exactly the same as this one, right? We keep this one open and this one closed. And this part of the buck converter is exactly the same as this one. Over here, there are some changes, okay? Because we have the switch that is going to be controlled by the on-off signal, right? But we do not have a diode. We have a switch instead. So if you recall the function in the cycle of the buck converter, when we close the switch, we had current flowing through the inductor this way, from the source through the inductor to the load. When we open the circuit, the diode was providing a conduction path, right, like here. So the diode was conducting only when the switch opened, but not when the switch was closed. So we could design a circuit that will make these two switches work in a way that when one is open, the other one is closed. So when we close this one, we open this one, and we have like the diode not conducting, and we have the same current path as in the buck converter. When we open this one, instead of using a diode, we just close this switch and we provide a path for the current to flow again. All right. So that's how this circuit can work as a buck converter. Now, as the battery voltage drops, we have to change the topology to work as a boost converter, right? And how do we achieve that? Well, we keep this switch closed at all times, right? And this one open. So that makes the input voltage connected at all times to the inductor, okay? And again, we do the same trick. This switch is going to be performing the same function as this one, and we replace the diode with another switch. So when the switch closes, we have a path over here through the coil to ground, right? And that's exactly the same that happens when this one closes, right? So we have a path through the inductor to ground. And then when this one opens and this one closes, in this case, the diode is going to be conducting the current to the load, right? But because we have no diode, when we open this one, we make sure this one closes, and that provides the path for the current in the inductor to go to the capacitor and the load. Very clever, if you ask me. Okay, so the same way you could purchase a linear regulator in a single package, you can also purchase a switching regulator controller in a single package, and it looks like this. So it's very similar to a linear regulator, only it has more terminals. These are also available in preset voltages or with an adjustable output. So here we have again the buck converter that I'm putting here for reference. And down here is how you would be using this integrated circuit controller in a real circuit, okay? So let's see how this works. Let's have a look at the output part here. We have a diode from ground to the output, an inductor and a capacitor. So if you have a look at this section here, it's exactly the same as this section here, right? So no surprises there. This resistor is missing because this would be representing the external load, so the device that we want to deliver power to, okay? Here we have a switch. The switch, of course, is the part that is, or one of the parts that is integrated into this circuit. So we have an input voltage here that gets connected to an external DC input, right? So that would be this part. Internally, we have a switch connecting the input voltage to the output that connects and disconnects several times per second. And we also have a ground connection here. Okay. Now the other terminal that you see here is this one, feedback. And feedback gets connected to the output. What does feedback do? So this is a 5-volt fixed regulator. So the feedback terminal is actually monitoring the voltage here at the output, and it is ensuring that this is working in such a way that it will be delivering 5 volts to the output, okay? So if for whatever reason it detects a bit less than 5 volts, this will increase the duty cycle, right? The on time related to the off time. And that's gonna raise the voltage back to 5 volts. And if it senses that the voltage is a little bit too high, maybe 5.5, this will decrease the on time and will bring the output voltage back to the 5 volts that we want. Okay, so if you're going to be designing some switching regulators, there are a few considerations that you have to keep in mind. The equations for T on and T off, the on and off time that I explained earlier, are based on ideal components. Like I said, in real components, when you have inductors with resistance and when you have diodes where the voltage drop is not zero when they are forward biased, you will have to compensate a little bit for the on and off times. The regular diodes that we studied for rectification are not good for switching power supplies for a couple of reasons. One is the response time. We need something faster. And we also need to minimize the voltage drop as much as possible. So there are some special diodes that are called Schottky diodes that are the ones that we would be using here. If we go back to the previous slide, you see these, that the bar on the diode has these waves here at the ends, right? It's like a weekly bar, I guess. You can call it like that. And that's the symbol for a Schottky diode. The other consideration that you have to keep in mind is that inductors and capacitors have to be able to handle the currents and voltages that are developed in these regulators. And the current through the inductor, depending on the topology, can be a lot higher than the current through the load. Okay, so keep that in mind. And something else that I don't have in this slide, but you have to keep in mind when you select inductors and capacitors is the frequency at these, that this is going to be working at. Okay. Because of all of these configurations, switching regulators are sometimes not very easy to design correctly. But fortunately, there are several companies that make pre-made modules that you can use, right? So the modules could come like a bare board like this one, right? If you have a look, you have here the controller with the 5 terminals. You have, this is probably your input capacitor. This is your output capacitor. This is your inductor. And right here, this little black thing looks like your diode. Okay, this is a potentiometer to adjust the output voltage, right? Because this is most likely an adjustable one. They can also come in an encased package like these two, right? And again, with fixed voltages or adjustable voltages. So this one would be used pretty much like a 3-terminal regulator. It's a little bit bigger, right? And but should be as easy to use as a regular one. So to recap what we saw today, switching regulators are much more efficient than linear regulators, especially at high currents, while linear regulators can have efficiencies in the 50 to 60% for high currents. Switching regulators can be in the 85% range or so. Switching regulators are available in different topologies that can increase, decrease, or reverse the voltage. And getting them right requires careful selection of components. But fortunately, they are available as pre-made modules. So if you need one of these, it may not be worth trying to design your own, but just get a pre-made one and drop it in your circuit. Okay, so that's all for today. I hope you learned about switching regulators, and we'll see you next time with a video on transistors. Thank you. Bye-bye.